Okay, in this example, we know that Harley-Davidson motorcycles make up 14% of all motorcycles in the United States. So we know that P equals 0.14. Okay, so that's the population proportion. Okay, and you're going to have a simple random sample of 500. So that's N equals 500. And we want, given that the average is 500, what's the probability that your sample will have greater than 0.2 or 20% Harleys, given that you know that it's 14% on average. So I'm going to switch the page here. So I'll rewrite those things in there. So we'll go to the next page. And so we know P equals 0.14. We want the probability of the sample of a sample having greater than or equal to 0.2 when you have samples of 500 motorcycles. So we've got our population sample as 500. So the temptation is to right away go do some stuff. Other than but we should think about it. What we need to do is think about, is this sample independent? Do you think, so we have to check for independence. That's the question. Is it independent? It's yes, as long, it is true, as long as the chance of any person riding a Harley is not influenced by another person, or doesn't change because another person rides it or doesn't ride it. As long as the people in the sample don't affect the probability of others riding a Harley. That's the first thing. The other thing is you also want to make sure that when you get someone's opinion or get someone's situation, in this case not opinion, get someone's situation, that it is less than 10% of the overall population, so you're not actually changing the independence. Because once you ask someone if they ride a Harley, you're not going to go back and ask them again. So we're going to also check the 10% condition. It's part of our independence check, and so 10% condition. So I would say the sample, they come, actually let's change that. Do you think it's safe to assume the sample of Harley, actually, sample of motor cyclists is less than 10% of the population of motorcyclists? Is that reasonable? The sample is less than 10% of, in other words, are there greater than 5,000 motorcyclists? So we had to check that condition. The other thing is we have to make sure that we're comfortable that a normal model might approximate this. So the second thing is, can we use a normal model? Okay, and to do that, what we need to do so in order to check if a normal model, the second thing we should check for is a normal model. In order to check if it's reasonable, we need to check our successes and failures. And so we're saying that in the population, we'll use the whenever we have a chance, we should use that one instead of that one. Okay? If we didn't know what this number was, then maybe we would estimate it with this number. But since we know it's this number here, someone's already told us that this is the right number for the population, we're going to believe them. And we'll use that and we'll say 0.14 times the population is 5, or the sample is 500, and see if that's greater than or equal to 10. And it turns out that that is 70, greater than or equal to 10. So it works, and that's really going to make sure then if you do 500 times 1 minus 0.14, that's also going to be greater than 10, because that's going to be 430. So that works. So we can use a normal model. So on the next screen, I'm going to do the normal model. Okay, so I started my normal model here. And one of the things we have to know is that how would we expect samples of the size 500, how would they, every 500 cycle sample, how might they be arranged here if we were randomly asking motorcyclists if they ride a Harley or not? So we want to see that, but we don't have all the stuff. So we know that the long run average is P, okay? But with samples of 500, we want the standard deviation, okay? Okay, so that formula was PQ over N. So I'm going to write 0.14 times 0.86 all over 500. When I do that, so I got the standard deviation is plus or minus 0.0155. So in other words, one standard deviation is going to be here, and one on the other side is here. Okay, so we're going to get 0.155. I'm just going to say a 6 there, and then we're going to subtract it as well. We get 0.124, and we can keep going. So what I did was, if you didn't follow, what I did was I just took my standard deviation and I added 0.156, and I subtracted 0.156. So that's the number I used right there. I just rounded it. Okay, so I get that. Actually, it's I just wrote the wrong number in. It is 0. There's supposed to be a 0 here. Okay, that's a 0.156. 0.156 here. I'll erase that. So that's going each side, and you can continue on doing that. So we've got that going there. Now we can go back to the question, which was, if we go back a couple screens, how likely is it that a sample will contain 20% or more who own Harleys? So let's go back forward and go to our picture here. I'll use a different color. 20% or more. Well, that's 15%. It's going to be way out here. That's 0.2. And they want this area here. This area here. Okay, well that should be fairly easy. We need to get a z-score. The z-score of 20% is going to be 0.2 minus the average. Well, or in this case the average is the population proportion over the standard deviation, which we said was 0.0155. Okay, So when I do that, when I figure that out, I get a z-score of 3.871. So to get this area right here, okay, that's my z of 0.2. It's going to be a really small number, so I'll get that area. You don't have to write this on the AP test normal CDF, you just have to do it. But I'm going to do it from 3.871 to infinity, which is, we'll use 9 on the calculator, and that gives me this. So it gives me this answer here. It gives me 5.42 times 10 to the negative 5, so 0.000, that's 454. Okay, that's pretty low percent. So how would I interpret this? There is only a 20%, sorry, there's only a 0.0054% chance a sample of 500 motorcyclists the 500 motorcyclists will have 20% Harley Davidsons. It's not very likely.